Okay, last time I guess I reached this point. Let me write it again. N 0 plus 0, So that's for simple linear regression with one predictor. And if you solve this, you will get these. Let me find it. So, okay, now, well, that's fine. So let's alpha 1 will be this thing. This one time, I think that's good. And over n, whoop, n. And over 0 will be minus d 1. So that is y bar minus if you plug in v1. Oh, it's v1, that's not one. See, this is y bar, this is x bar. Okay, now, well, we usually don't write alpha 0, alpha 1 here because these are things that we assume they are fixed in a sense. So these are in fact the things that we calculate through this thing. And most books use this. So you will see that these are in fact themselves some kind of random variable. I will show you. And then the realization of those random variables will be B1 and B2. So instead of writing, so they will become random variables B0 and B1, and with realizations B0 and B1. Or some books use hat on top of these things. So in practice, you don't really see too much difference unless you delve deeper into the theory. In practice, you basically do this. You just, to most people, they don't even know the difference between these things. So, but anyway, no. These if you fix the xi, then yi will be, well, we assume that y with values yi's, then that is a random variable. So this can be, let me increase this thing here. And if let me see what the book uses. So, this one, as I said, it's a random variable in this form, b1. If I set this to be simplified, we will get this. In fact, this is like a variance, so on top I will get this. Let me copy from the book, sigma xi minus x bar times I minus y bar. Divided by, and divided by sigma xi minus x bar. You can, if you are interested, in fact, this, if you expand this, then you will get this, or if you expand the other one, you will get this. So now this one will be, let me write it like this. So I have sigma I from 1 to n xi minus x bar times yi minus. This y bar is like a constant. There is no I here, so that's sigma I from 1 to n xi minus x bar. Okay. So what the denominator stays? Denominator is simply I from 1 to n xi minus x bar squared. Now this guy here is 0, right? The sum is 0. Let me show you why it is 0. So but I know 1 over n sigma I from 1 to n xi is x bar, right? So that is sigma xi I from 1 to n is n x bar. So if I move it to this side, I have sigma xi I from 1 to n minus n x bar is 0. I can bring this inside. So it's like x bar minus x bar minus x bar n times. So I can write it inside this. So that sum is 0. So this sum is 0, therefore we can get rid of that part of this guy here. And I can just remove. So that is B1 and B2. So this one, sorry, B0, and that is, what did I have? Let me check, and that was B0. I can't find y bar minus B1 x bar. So that's y bar minus B1 x bar. So claim B0 and B1 are unbiased estimators of which means the expected value of B0 given the xi's. In fact, well, I have given a proof in the notes, and you will see the xi's come into the picture and then that just go away. So I'm not going to write xi's, but this is given the xi's is in fact alpha 0, and the expected value of the other one, B1, will be alpha 1. So these are unbiased estimators for alpha 0 and alpha 1. And we also need the variance of these two because we will develop a confidence interval for these random variables. In fact, this is the expected value, but that's the mu. That's so the confidence intervals for this, for alpha 0 and alpha 1. So these are the means of B0 and B1. So this is in those notes. You can just check. Or you can try if you like. You can try to find the E. If you apply E here, these are just constants. So E is applied to yi, and also in the denominator, these are just constants. It's not that hard to prove. But we can also find the variance of these two and the variance of B1. And I also have given the formulas and the derivation of these two formulas in the notes. So let me sigma squared over, I guess that's the normal sigma well, sigma squared was sigma squared. Remember the epsilon i's, epsilon or epsilon i's, we were n 0 sigma squared. So it was the variance of the errors. And we assume that they are the same. And we also will assume that the epsilon i's for are in fact independent. And the variance of B0 will be, what is it? So, I think sigma xi squared. So it's sigma xi squared on top divided by n, n times this. Okay, so these are the variances of these two random variables, and the means are in fact alpha 0 and alpha 1. So anything that we say, like if we use, say, confidence interval, that confidence interval is for alpha 0 and alpha 1. We will see that. Or if we do test of hypothesis, which I will tell you what it is, but the test of hypothesis, in fact, is the null hypothesis is that alpha 0, alpha 1, or whatever they are, the other ones are 0. So that's the null hypothesis, and you check that. So I will explain that when I discuss R and the output of linear model in R. So let me erase this thing. Okay. And also, I have given the proof for that sigma square. So I have given this S squared equals yi minus y hat I squared sigma over n minus 2. That is n unbiased estimator of sigma squared, which was variant of epsilon noise. Okay, so and y hat, that's the calculated I. That's calculated y I. So let me show you in picture what this thing is. So let's say this is these are like x I y i's that I have, and this is the. Let's see if I can. If this is. You can use that. So let's see this one. So this might be the regression line. Take this one for example. Say this one is xi and yi. This is the data point, and I have xi here, and this is y hat I. So this point will be xi, comma y hat I, which is on the regression line, and this is the residue. From here to here is called the residue, and you can see these are in fact these differences. So this is the sum of all these differences that we have here. So this one, then this one, then say this one, then this one, and this one, and this one. So that is the sum of those differences squared. Okay, so it's like those are like 2 points in the n-dimensional space, and you're finding like the distance between them, say. So one of them has coordinates y1 up to yn, the other one is y hat 1 up to y hat n. You find a distance and you square it and divide it by n minus 2. So it's like that. So if distance squared divided by n minus 2. And you will see, in fact, I have proved this in more general situation. That's for multilinear regression. The proof is not easy, and this is a special case of that, which I will write it here for you. And it's not an easy proof, but anyway. So this is in fact what estimates that sigma squared. Okay, now let me erase this. So this y hat will be like y hat I will be something like this. If I have calculated, or what I have calculated is b0 plus b1 xi. Now in some books they use this xi. So that's like the calculated. And in fact they use beta, not alpha. So let's use alpha because I used alpha. I should have used beta, but that's like alpha bar. Alpha hat, so alpha 0 hat, and alpha 1. Anyway, so the picture is more important than just writing out some formulas. So that's what we found. Just these differences and square them and divide by n minus 2, and that is the best approximation to sigma squared. Okay. So let me. And also you can see this thing. Variance is what? Variance is in fact something like that, right? So variance of some random variable was like e of x minus ex squared, right? So, and you can see something, I'm not saying exactly similar, but something over there, especially the square, and then there's like y minus ey, something like that. But anyway, so, okay, now, let's see. Now, let me see what next. So, inference on regression coefficients. And I'm not going to give you, okay, so this is, we are using a t-distribution here. This is for alpha 1, so we use the t-distribution, and that is in fact this. What is this thing doing? There, so b1 minus alpha 1 times sxx sigma over s square root of xx sigma over divided by s over sigma. Now this s is in fact the s I found, so this s is the square. So sxx is this. Sxx is this one, the xi minus x bar squared. So that's sigma xi minus x bar squared to n. So that's like the x squared, ex squared that we have in a variance formula. And then we have sxy, which is sigma, I think that's also the same thing. X bar y minus y bar. Okay, so we are using t-distribution, and well, let me erase this. These are all in your textbook, you can check. And confidence interval for alpha 1, in fact, is, we say that alpha 1 therefore belongs to this interval that I am going to write. That is the B1 that we have found. So this is what we have calculated for alpha 1 minus the alpha over 2 times s over sigma sxx, comma b1 plus this. Let me check. Yeah. So, and then this s is in fact the calculated value for that s. And this has a t-distribution. So t alpha, it has t-distribution with n minus 2 degrees of freedom. So t alpha over 2 comes from t-distribution with n minus 2 degrees of freedom, and the bi's, b1s, or the b1 is what you calculated, and that is the confidence interval. So with 100 times 1 minus alpha percent confidence, alpha 1 belongs to this interval. So this might be 95%, 99%, or 0.95, so it means with probability 0.95, this guy, alpha 1, lies in this interval. So if you change that to 99%, you're changing the T alpha over 2. So you will get a wider interval, much lower. Okay. So this is for alpha 1. Now if you, in fact in R calculates this thing. R calculates this thing. I will explain that. So let me for alpha 0 is different, but I guess R also calculates for alpha 0. It is a little different. Copy this one, I can't remember. So the T is this. For alpha 0, we have T is B0 minus B0 that we found. So this is what we calculated. And over S square root of something. Sigma xi squared minus xi. So again, you see we are using T, so that's also the equals T distribution. So, and there is some interval which looks like this, but I'm not going to write it. So that alpha 0 will belong to a certain. This is alpha 0. That alpha 0 belongs to some interval which you can look at the textbook and see for yourself. Okay. Now for test of hypothesis, the same statistic is used for both of them. And you don't really need to know what that is, except to interpret what R gives you, because R really gives you what we call the p-value. And it also gives you something like this. So let me erase this thing. So the output of R is this. Let me look at this output here, and so I do not give you something. Where is it? I'm trying to find. Okay, so it's somewhere in R. Let's see in R what happens. So in R, this linear regression is called LN, linear model. So inside this linear model, you say, for example, the data set was the price of houses, and each house, the price was recorded, and some other things like number of rooms, number of blah blah, square feet of the whole, the building, square feet lot, square feet blah 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 blah. So one of them might be this, that you want this. So you write price until you can say square foot say lot. And then you say data, and you write the data, which is a data frame in R, and you can take a look at the notes that I posted. It's in R Markdown format, so you can see how this thing works. And this means that the price, which is like the Y here, and this is like the X. So it means that Y, in fact, E of Y given X is some alpha 0 plus alpha 1X. Okay, so this means that all Y is alpha 0 plus alpha 1X plus some epsilon. Anyway, so this is what it means, and so when you enter this and you run it and you ask for summary, so you enter something like this and you say, okay, you give your model some name, my model, and when you ask for the summary of the model, I never use space between two words, always use an underscore. So when you say summary, it will give you some certain things, like the residues, the minimum, maximum, and the median, and maximum residue. Remember, residue was the difference between the calculated y and the real y, the data point. So those are residues, and it also gives estimates. So the estimate one, it has estimate on top, then it has STD error, and it has T and T value, and this is P. It has it's something like this: P of bigger than. So the estimate, the first row is intercept. Intercept is alpha 0. Alpha 0 in our notation. Then it has, so since this guy is like this, so let me write it here. So we are saying that price is alpha 0 plus alpha 1 times SQFT of lots. So here it says SQFT plot, and it gives the estimates. So the estimates are in fact alpha 0, alpha 1. In fact, these are not alpha 0, alpha 1. These are that B1, B0, B1. The values that are assigned to the B0, B1 are realizations of those two random variables. Now, STD error is that S divided by square root of n. N is the number of data points. So if it's 100, that's square root of 100. And T value is that T I guess it is 95%. So that's T of 95%, T of alpha over 2. And no, I guess this is, let me see, no. That's in fact, that is, I guess that is some, I think that's T alpha 0. No. Yeah, that's the estimate divided by this, I guess. Yeah. So that's the estimate divided by this. Well, let's check this thing. And this is the p-value. Now the p-value is, when it says p bigger than this t, the p-value is based on the null hypothesis that alpha 0 is 0. So, or in fact, this one makes more sense. Alpha 0 is 0, that's not important. This alpha 1 and so on are important, the rest of them. So, it's saying, okay, we can interpret like this. Say, how far is this alpha 1 and alpha 2 and so on? How close are they to 0? If, say, this alpha 1 is 0 or close to 0, then the regression line looks like this. See, as the regression line gets closer and closer to a horizontal line, it means that this y doesn't depend on x. So there's basically no dependence. It's just like this x, whatever the x is, y is just a constant. So it's important to check this and see whether it is close to 0 or is 0. So the null hypothesis is based on this. Now, when it finds the p-value is like a probability here. So it finds the probability of this bigger than this t. This x, the random variable, bigger than this. And it's like, I don't know, a picture for you. So if that is the t distribution and you have this thing here, and here. So it's finding the probability that it is here and here. So this is like the t minus t, and this is like the t. So this t and bigger than this is bigger than t and less than minus t. So it's finding the probability of being here and here, both of them. So if this is a less than certain value that you have in mind, usually it's, if it is a small number, R will give you some indication that this is okay. So, and if it's like 10 to the power negative 16, then it has some stars here, like 1, 2, 3, I guess it's like 1, 2, 3, something like that, yeah. Okay. So here in this example, it is 1, 2, 3 is for 0.001. So 1, 2, 3 is for 0.001. That's very small. So when you see these stars, it means that it's okay. So in fact, that's not close to 0. Although you might see that it is 0.05. 0.05 is okay. I'm not saying it's bad. It depends on the situation. It depends on the data that you have. But anyway, so this, if this is small enough, then you can say that yeah, this is significant and acceptable. So it's good. Now, in this example that I guess I have posted for you, this p-value for the intercept is 0.574, which is way too much. And in fact, if you look at the estimate, you will see 0.049, which is very small. Compared to the numbers that we have, it is very small. So intercept 0.05, 0.05 is almost here. So it means that the line starts here, which makes sense if you have a house without any area that is square foot of blah, blah, all of them 0, then the house has no value, right? So even this line or this calculation tells you that this is almost 0, which is the intercept. So this is price, say, and this is square feet of the lot, right? So if this is 0, then there is no house. So what value? So it makes sense for this y-intercept be close to 0. And p-value is so large, it's like 0.57. And it says it's not significant, so you can ignore that, and it's not good anyway. But you can interpret, because, well, I know, I just throw this away. There is no alpha 0 here, it doesn't make sense. There is only alpha 1. Because if this is 0, this is 0, so this should be 0. Anyway, so this is if there are other things given here, you can Google and find out what they are. So I just leave that to you. That's like your homework to figure out. And also read, it is good to know some test of hypothesis, although you, as computer scientists, you probably will never see that. You will see mostly linear regression itself, not that, and or machine learning or deep learning or other methods which basically there's no test of hypothesis like that. Even if there is anything, it is Bayesian version, not this version. Okay. So let's see what happens in multi-variable regression. Multi-variable is like this. So I have some multi-variable in front of me. Multilinear. So we have predictors xi, kx, and y is just one y. So we are predicting the value of y, and we just if, and I explain this thing. This is the theory. So the theory says that if the xi's, so this is how it works. If the xi's are like this, so if I have y and xi's, xk and y, if they have normal distribution, and that's k plus 1, so if they have normal distribution, multivariate normal distribution, and if the xi's they also have some normal distribution inherited from this, and if they are independent, if they're independent, then we can prove that E of y given this xi's, xk, in fact it looks like this. So we can prove that. We can prove that the y, the expected value of y, or the mean of y given the xi's, is linear. So that is in fact the best situation. The best situation. If they're independent, remember I in fact told you that if I have certain random variables with joint distribution being normal, then they are independent if and only if the covariance between xi and xj is 0. So it means the covariance matrix is IMO. But in practice, that doesn't really happen. So there might be some correlation or covariance. In fact, I will tell you what correlation is. There is correlation between them. So this is just an approximation for in just any y and x's. So what happens here, even in this situation, it means that y is in fact alpha 0, alpha k xk, plus some error epsilon. Okay, so these are all normal, so epsilon is normal, and you assume that epsilon, you can assume that epsilon has, because this is like a mean of this thing, so if you take the mean of epsilon will be 0. So epsilon has mean 0, and so we can assume that epsilon from, say, experiment to experiment, variance of that doesn't change, so it stays sigma squared. And that again doesn't happen too often, but when you assume it happens, then things get much nicer. You know, we are just making certain assumptions, which perhaps doesn't happen in practice, but those assumptions make life easier. At least they give us some model, like this model, for example. Anyway, so we just say, okay, we take this. Although usually these are not independent or even not normal, this is not normal, it might be something else, or we can never really associate any distribution that we know to these things. So anyway, so that is our assumption, and when we do experiment, we in fact, the book uses a B, so that means B. So I do some experiment. So I have like several students, and I give them those predictors, the XI's. It's like, say, you're trying to find the effect of certain medication on some patients. So they administer those medications, certain dose, and to different people and see some certain reaction, like if it is like blood pressure, so you check the blood pressure or something like that. So the Y might be something like that, blood pressure, or say blood sugar level or something like that. But anyway, so the Y, the instances of Y will be Y1, Y2, and Yi in general, and I have B0 plus B1, X1 plus up to BK, XK. Okay, so that is the predicted yi using the predictors and the values given to the predictors. Now how do we find those? Now, we do the same thing that we did, that residue. So, list works. So remember that MSE that I wrote the MSE was sigma of, say, it was a y minus yi. Okay, well, let me double check and see. In fact, that's correct. So yi minus, that's yi minus that y. Okay, square. So I from 1 to n. So we have m students. So this is in fact the y hat. So we have sigma I from 1 to n, y I minus alpha 0 y x1. And so it will be, this x will be the x that you have given to the ith student. So we have to use 2 indices for that. And the convention is like this. So it is alpha 0 x 1i alpha, so that's minus again, minus alpha 1 x 2i minus dot 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 minus alpha k x ki squared. Okay? So this is like a function of the alphas. So we want to find the alphas. Alpha 0 up to alpha k. These are like the function of, let me see. Why do I use alpha? So I should use b. But that's the b. So this is like a function of the b's. B0, B1, these are bk. And so this is a function of bi's. So we want to minimize this, MSE. And I made a mistake last time, that's just a silly mistake. In fact, this is convex itself. Y x squared is convex, not x minus x squared. This is convex itself, and being a convex function, it has an absolute minimum. So whatever method we use, we should get an absolute minimum, or at least get closer to the absolute minimum. We use this simple methods from multivariable calculus, and so we find partial derivatives. So we have partial derivatives b, say this f, while d bi equals 0, and I starts at 0, goes to k. So we set them 0, and we solve for bi's. And since, as I said and say it again, that's convex, so whatever we solve for definitely will give us minimum. Okay, so if we do this, we will come up with this nice matrix. So, well, I have given all of that in. So in the end, we will get something like this. The y is some x times the b's plus some epsilon. And the x, it looks like this. It has 1 from that goes for b0, and then it is x1, x1, 1, 2, 1. So what is x1, 1, x2, 1, xk1. So that's for the first row. That is alpha b0, b1, b2, b0 up to bk. That's the first student, and the second student x. Let me say 2, 1, 2, x2, Q2 up to xk2. And you see the indices are different from the indices we usually use for a matrix. But that's okay. Then that's the second student, and the last one will be x1n. Did we assume that it's n? No. x1n and x2n up to xkn. So that's the x. The y will be y1 up to yn. And the b will be b0, b. In fact, bk. The y. So, and epsilon will be something like this, epsilon 1 up to epsilon n. Okay, so if I ignore the epsilon, I have an equation like this. Y equals xb. And this is vector. And usually this has more equations than unknowns. So it might be 10,000 equations in 10 unknowns. So that is, we cannot solve it, right? But we can solve the, remember the least square method, which I can't remember if I explained that from linear algebra standpoint. But anyway, so this is what we do. So we have x b is y. So we want to find this. So we use the methods that we had, and this is what happens. Well, this is not. So that matrix was how many rows I had? N rows by k plus 1, right? So this is not a square matrix. So I cannot invert this matrix, but if I multiply it by its transpose and multiply this one by x transpose, so I will get this xd b x transpose. Now, if columns of that matrix, if they are linearly independent, then this x transpose x is invertible, and I will find the b's. So the b's will be x inverse, x transpose. So this one is called the normal equation, and the normal equation has this solution, and those are in fact coefficients. Now, what else can I say? So this, what happens in practice, first of all, they usually don't really solve like this. So when they minimize, they don't find the derivatives or something. And most often they are in fact solving a Lagrange multiply equation. So they call it the ridge, say ridge regression or lasso regression. So they minimize MSE given something. So that's like a Lagrange multiplier problem, and so the MSE, something is added to MSE, and then they should, if you want to try that, if you want to find D, say D MSE over D alpha I, that is some big mess. So what they do, they in fact find that, that's not what I'm saying, but when they want to solve, they use other methods to find the minimum, and so there are some numerical methods, like gradient descent, for example, or stochastic gradient descent, or some other things, that some of the methods they use to find the minimum, or at least get closer to the minimum. Especially when the matrices are huge, like 10,000, that's a lot, that's a huge matrix, so you don't want to waste computer time and do this calculation. This is so messy. No, not messy, but it takes time. But anyway, so this can give you, now if you have a small matrix, which on the at least the data set I gave you, or the data sets that you deal with, are perhaps very small and compared to what they have in real life. And there's another thing which happens here. If I have more predictors than data points, so if this X that I have here, which was like this, 1, then it was K1, for example. If I have, if this is bigger than this is bigger than this, which means I have more predictors than data points, then you cannot invert this, you cannot do anything. And that is the situation that is happening in the past few years. It's really happening, and you have more predictors than data points. In some areas that I haven't seen, but I have heard in like genetics, for example, they have like, they say million, right? I don't know what million means. So million predictors, maybe other, and very few data points. So they have to use other methods to find a solution to an equation like this. So this equation only works if these are linear independent and if you have more data than predictors. So if you have like 10,000 here and 10 here. But if you have 10 here, 10,000 here, then no way. Okay, so there isn't much left here except when you do multilinear regression again on R, you will get the alpha I. So just simple linear regression, you have alpha 0, alpha 1. If you have like 10 predictors, you will get alpha 0 up to alpha 10. And also the p-values and so on. And you can just look at the p-values and see which ones are good. And so that's, I guess, all about linear and multilinear regression. I have posted some notes on regression, in fact, and I was in a hurry to post them. So they are okay, but I should make some changes to make them more usable by students at this level. So, and also I posted other things on D12, so you can check that. And okay, so see you next time, next week, say, and stay home. Bye.